Yeah. Okay, so on this packet, I've got a couple of different data sets we'll use for the rest of the week. Let's take a look and work through together what's on the first page. All right. 12 different sandwiches at McDonald's were measured for both their protein and fat content. We're interested in predicting, analyzing any relationship between protein and fat. This response variable. If there are any changes in the fat content explained by variation in the protein content of these sandwiches. Our X values have an average of 17.2 grams and a standard deviation of 14. Our Y values, our response variable, has an average of 23.5 grams and a standard deviation of 16.4 grams. The correlation coefficient, the R variable, is 0.83. So let's do a couple different things. For part A, it says calculate the slope of the regression line to predict fat content from the protein. So the slope formula from that video, or also on the back wall behind Jaden, I've got all the notes for S11 back there, is equal to the correlation coefficient R times S of Y over S of X. The average spread in Y over the average spread in X. Mm-hmm. So if we just take our summary data, we can calculate the slope for this regression line to predict fat, our response variable, from protein. .83 times, let's see, S of Y is 16.4 over S of X, which is 14. Grab a calculator, let's get that typed in. 0.83 times 16.4 divided by 14. About 0.972. Regression line has a slope of approximately 0.972. What does that mean in context? What's the interpretation of that slope value when we talk about these sandwiches from McDonald's? I put a lot of the interpretation for all of these different values on the back wall, but it's like in the general case. Instead of using the names of the variables, I'm just calling them X and Y. Slope is the rate of change, so as X changes by 1, Y changes by our slope amount on average. That's the general sentence. What are we actually measuring X and Y in for this particular set of data? X represents what?
Protein.
The protein. Y is the fat. So instead of using X and Y, name those variables. As the amount of protein changes by 1 gram, as the protein increases by 1 gram, what's going to happen to the fat content?
Increases by 0.972.
As X changes by 1, as protein increases by 1 gram, fat increases by 0.972 grams on average. There's some variability. Some sandwiches are going to have higher fat content. Some sandwiches are going to have lower fat content for a given amount of protein. But on average, fat increases by 0.972 grams every time protein increases by 1. What's the direction of this set of data? Is it positive or negative?
Positive.
Right. Isn't R positive? Isn't the slope of our trend line a positive number? So as protein goes up, we should expect a similar increase in fat, which we've seen so far. Part B asks us to do the y-intercept and explain its interpretation. Y-intercept is a different formula. Y-intercept formula is y bar minus m times x bar. Our B y-intercept value is y bar minus the slope m times x bar. So since B is defined in terms of the slope, I have to find the slope before I can find the y-intercept. That's why we did part A first. Every trend line goes through x bar comma y bar. So I know it has to pass through this point. Using the given slope, I can find the y-intercept like they explained in the video. So y bar is 23.5 for our given set of data. The average fat content is 23.5 grams, minus the slope, 0.972, times the sample mean in the protein amount from these 12 sandwiches, 17.2 grams. Another calculator here. 23.5 minus 0.972 times 17.2 is 6.782. Y-intercept. What does that look like for a line? Describe what the y-intercept is for any line. Slope is the rate of change. The y-intercept is the
X is equal to 0.
so it's on what axis?
Y.
The y-axis. The y-intercept is where the line crosses the y-axis. To be on the y-axis guarantees that x has to be 0. So in general, to interpret the y-intercept value, we use this statement. When x is 0, the predicted value of y is our y-intercept v. We'll just replace x and y with the variables we're using. X is measured with what variable? Protein or fat? X represents what variable? Protein. When the protein amount is 0 grams, we expect the fat content to be about what number? 6.72 grams. For a cheeseburger with no protein, it should have 6.782 grams of fat. And what that means. When a sandwich has 0 grams of protein, we predict it to have 6.782 grams of fat. I don't know what kind of sandwich has 0 grams of protein, but it is what it is. Typically, that y-intercept doesn't have a whole lot of meaning in context, but it is important to understand what y-intercept represents for a line. All right, moving on. Letter C on the bottom half of this page says, calculate the R squared value. Let's just do that right here. R squared. R squared is called the coefficient of determination. It tells us how good our trend line is at fitting the data. The closest the R squared value is to 100%, the better the fit. The more it explains the relationship. The closer to 0%, the less good of a fit. It's not going to explain the model. It's not going to fit the scatter plot. How do I find R squared? Square R, right? What's our R value? 0.83. So shouldn't R squared just be this R value, 0.83 times itself, squared? I have another video for us to start class with tomorrow that gives us a bit more background and meaning behind R squared. But for now, R squared is really just taking the correlation coefficient times itself. So 0.83 squared is 0.6889. To interpret R squared, it's a new statement down here. R squared tells us the percent of the variability in our Y response variable that is explained by the variability in our X variable. Once again, replace X and Y with the variables we're using. Y is what? Fat. X is the protein. So 68.89% of the variability in the fat content is explained by the variability in the protein amount. In fat amount is explained variability in protein for these sandwiches. 68.89% of the variability in Y is explained by the variability in X. So 68.89% of the variability of the fat in these sandwiches is explained by the variability in their proteins. All right, let's do part D. Write the equation of the regression line. Regression line is Y hat. The predicted amount of Y is equal to M times X plus B. Well, I need to define this in terms of the slope and Y-intercept that I've calculated. What was our slope? 0.972. So replace M with that value. Y hat equals 0.972 times X plus our Y-intercept, which was 6.78. You might see a regression line like that in terms of X and Y. They might also write it using the names of the variable. So they're going to replace Y with the fat. They're going to replace X with protein. So you might also see it written like this. Fat hat, the predicted amount of fat in a cheeseburger, is equal to 0.972 times the protein plus 6.78. Might also see it written in terms of the variable using its actual name. Questions on anything from this first page? Finding the slope, finding the y-intercept, writing the equation. As long as you have these formulas, right? It's not too terribly difficult, I hope. We've seen the video to explain where this comes from, and now you're just using them for a particular set. Flip it over. Let's look at the back of that first page. I'd like you to answer questions 2 and 3 on your own before we try it and explain it together out loud as a class. Number 2, predict the amount of fat for a burger with 19 grams of protein. So what are you going to do? Didn't we just spend all that time writing an equation to predict the fat for any sandwich I want? Well, now there's a sandwich with 19 grams of protein. So plug in 19 to your equation. We spent all that time making it. Now let's use it. Number 3, a burger at McDonald's has 25.2 grams of protein and 43.5 grams of fat. What is the residual? I haven't really used the residual yet in class today. The residual is the difference from what we've expected. Take the actual fat content minus the expected or predicted fat content. A positive residual would indicate that it has more fat than I thought. A negative residual would be it's less fat than I would have expected. Grab a calculator. Find the amount of fat for a sandwich, or the prediction of the amount of fat for a sandwich with 19 grams of protein, rather. And then what's the residual difference for a burger that has 43.5 grams of fat when it has 25.2 grams of protein? Grab my calculator here. We've got 19 grams of protein. So 0.972 times 19 plus 6.782. Remember right, is that 25.25 grams?
Yep.
You should expect on average 25.25 grams of fat for a cheeseburger with 19 grams of protein. How'd you do, F?
Yeah.
What's the residual? How do you find the residual? It's the difference, but it's a difference set up specifically so that a positive residual tells you it's more than you would have thought. A negative residual says it's less than you would have.
Negative. Wait, no.
How much fat does this cheeseburger actually have?
42.5.
Okay, you got that. So I'm going to take the actual fat content minus the expected fat content. Do I know how much I predicted
Oh,
the fat content for this cheeseburger to have?
yeah, 31.
How'd you get that, Isaac?
I just plugged it into it.
So I have to know what I would have thought this cheeseburger was supposed to have for its fat using 25.2 grams of protein. For a cheeseburger with 25.2 grams of protein, how much fat do I think it's supposed to have? That's what I'm missing, right? So you plug 25.2 into your equation, right, Isaac?
Yeah.
Okay, so let's do that. 0.972 times 25.2 plus 6.782. What was that number? 31 something?
764.
So take the difference. This sandwich actually has 43.5 grams of fat when I expected it to have 31.27 grams of fat based on it having 25.2 grams of protein. It has more fat than it should. What's this positive residual equal to? How much more fat does this sandwich have? 12.22, 12.23, around like I had. Use them right there, man. That's fine. What does this number mean? One more time. What does this residual tell us?
The difference is more.
Right. For the amount of protein that this sandwich has, it has 12.23 more grams of fat by the top. Maybe it's got an extra slice of cheese or something like that. So it's got more protein, or it's got more fat than the protein should tell us. I had to find the expected amount of fat first based off the protein before I could calculate the decision.
How that work?
Okay, grab your laptops, please. Let's get on to Schoology. I'm going to open up some practice problems.
Good.